We begin our discussion of section 6.1, Wilson's theorem and Fermat's little theorem. We start with Wilson's theorem. Please take a look at this. Wilson's theorem says that p minus 1 factorial is congruent to -1 modulo p, if and only if p is prime. So once again, this is if and only if statement. Means if p minus 1 factorial is congruent -1 modulo p, then p is prime, and vice versa. If p is prime, then p minus 1 factorial is congruent -1 modulo p. So we have to prove this theorem in both directions. We want to prove that this implies this, and this implies this. Before we discuss this example, note that what is written here can be rewritten in the following way. P minus 1 factorial plus 1 is congruent to 0 modulo p. So Wilson's theorem in particular says that if p is prime, then p minus 1 factorial plus 1 is divisible by p. Now let us discuss examples. Let us check if this is true for particular values of p. Please take a look at this. If p is equal to 2, p minus 1 factorial plus 1 becomes 2 minus 1 factorial plus 1, which is equal to 2, and 2 is divisible by 2. Next prime number, 3. 3 minus 1 factorial plus 1 is equal to 3, and 3 is divisible by 3. To the contrast, 4 is not a prime number. And we see that since 4 minus 1 factorial plus 1 is equal to 7, this is not divisible by 4. Next, p is equal to 5. 5 is a prime number. And we see that p minus 1 factorial plus 1 is equal to 5 squared. 5 squared is again divisible by p. P is 5. Next number, 6. 6 is not a prime number, and indeed we see that p minus 1 factorial plus 1, if p is 6, is not divisible by p because it is equal to 11 squared. And so on. I highlighted in red expressions where p is prime. Expressions in black are expressions when p is not prime. We see that each time p is prime, p minus 1 factorial plus 1 is divisible by p. And each time when p is not prime, p minus 1 factorial plus 1 is not divisible by p. Our proof consists of two parts. First, we prove that if p is prime, then p minus 1 factorial is congruent to -1 modulo p. Then we will prove that if p minus 1 factorial is congruent to -1 modulo p, then p is prime. So, part 1. Suppose p is prime. If p is equal to 2 and p is equal to 3, the theorem is true. Just look at row number 1 and row number 2. Now let p be a prime greater than 3. By theorem 1, from section 4.2, each integer a, which is greater or equal to 1, and lesser or equal to p minus 1, has a unique inverse, which is again greater or equal to 1 and lesser or equal to p minus 1. Here is why. Please take a look at this theorem from section 4.2. It's over here. This theorem in particular says that if b is equal to 1 and a and m are relatively prime, the congruence ax is congruent to 1 modulo m has a unique solution. But remember what is inverse. Inverse of a modulo m is a solution of the congruence ax is congruent to 1 modulo m. Since this congruence has a unique solution, inverse is unique. Once again, by theorem 1, it has unique solution because it says if d divides b, note that if a and m are relatively prime, d is equal to 1. And since d is equal to 1, 1 does divide any integer. So this is true, but then it says this has exactly d incongruent solutions. Since d is equal to 1, exactly one solution. So by theorem 1, inverse is unique. Let us denote inverse by a bar. Repeat once again. For each a that satisfies this, there is a unique a bar such that a times a bar is congruent to 1 modulo p. By the way, the reason why the greatest common divisor of a and p is 1 is the following. P is a prime number and a is greater or equal to 1 and strictly lesser than p. It is lesser or equal to p minus 1. Since a satisfies this double inequality, the greatest common divisor of a and p is 1. It's exactly what is written here. Since the greatest common divisor is 1, the congruence ax is congruent to 1 modulo p has a solution. Moreover, the solution is unique because the greatest common divisor is 1. Any questions?
Sorry,
Yes.
I missed this. What was the definition of inverse?
Definition of inverse is over here. Inverse is an integer solution of this congruence.
Oh yeah, sorry, that just missed my mind.
So, since a bar times a is congruent to 1 modulo p, a bar is inverse of a. We just replace over here x by a bar.
So how do we know that a times the inverse of a is congruent to 1? Is this the first time we encounter that?
Well, we say that an integer number such that a times a bar is congruent to 1 modulo p exists. How do we know that it exists? We use theorem 1, or we can use the corollary. The corollary says that if a and m are relatively prime integers, this congruence has a unique solution. Know that in our case, a and m are relatively prime. Take a look at this. This is a, m is equal to p. Since A and P are relatively prime, and they are relatively prime because P is a prime number and A is between 1 and P minus 1. They have to be relatively prime. There is no escape. P is divisible only by 1 and by P. A cannot be divisible by P because A is lesser than P. So the greatest common divisor of A and P is equal to 1. Therefore, this congruence has a solution, moreover, unique solution. So A bar that satisfies the equation AX is congruent to 1 modulo P exists. You see what I mean?
Yeah, except for that. So why is the solution the inverse of A?
We call such a number inverse.
So that's by definition if it satisfies AX congruent to 1.
By definition of inverse. Inverse is a solution of this equation.
Oh, okay, I see.
No, but this is exactly what we have. Or replace A bar by X, we'll get AX is congruent to 1 modulo P. Solution of this equation exists. It is unique. Let us denote solution by A bar. We call A bar inverse of A modulo P. Does this make sense?
Yes, I see it now. Thank you.
Here's what we do next. Now, let us go back to Theorem Q from section 4.2. Here it is. This is Theorem Q from section 4.2. This theorem says that if P is a prime number, then A is its own inverse if and only if A is congruent to 1 or congruent to -1 modulo P. Once again, let us discuss what this means. A is its own inverse modulo P. A is its own inverse modulo P means A square is congruent to 1 modulo P. This means this. So by Theorem Q, A square is congruent to 1 modulo P if and only if A is either congruent to 1 modulo P or A is congruent to -1 modulo P. Let me reformulate what I just said. Think about the congruence A, X is congruent to 1 modulo P. Theorem Q says that X is equal to A if and only if A is either congruent to 1 or -1 modulo P. This is why we come up with this conclusion. The only positive integers less than P that are their own inverses are 1 and P minus 1. Because if we consider all integers from 1 to P minus 1, the only two numbers that are congruent, and remember over here, they should be congruent to either 1 or -1 in order to be their own inverses. The only two numbers that are congruent to 1 or -1 modulo P from this list are 1 and P minus 1. 1 is congruent to 1 modulo P, and P minus 1 is congruent to -1 modulo P. There are no other numbers from this list that are their own inverses. So once again, there are only two numbers from this list that satisfy the following congruence. A square is congruent to 1 modulo p. These numbers are 1 because 1 square is congruent to 1 modulo p, and p minus 1 because p minus 1 square is congruent to 1 modulo p. There are no other numbers from this list by Theorem Q. So once again, it is easy to understand why 1 square is congruent to 1 modulo p. It is easy to understand why p minus 1 square is congruent to 1 modulo p. What is not so obvious, why there are no other numbers from this list such that a square is congruent to 1 modulo p. In order to prove this, we need Theorem Q.
And could you just reiterate how we use Theorem 2 to show that there's no other numbers?
Please take a look at this. It's written, the positive integer a is its own inverse modulo p if and only if a is congruent either to 1 or -1 modulo p. Note that the only two numbers from this list that are congruent to either 1 or -1 modulo p are these two numbers. There are no other numbers from this list that are congruent to either 1 or -1 modulo p. Does this make sense?
Yes, thanks.
I still don't quite see why you know immediately that 1 and p minus 1 are the only two possible solutions to a is congruent to 1 modulo p.
Very good question. So, suppose a is congruent to 1 modulo p. This means a minus 1 is divisible by p. But since a is strictly lesser than p, a minus 1 is divisible by p only if a is equal to 1. Means a minus 1 is 0. 0 is divisible by p. And then a is congruent to -1 modulo p. Means a plus 1 is divisible by p. But a plus 1 is divisible by p only when a is equal to p minus 1. If a is lesser than p minus 1, a plus 1 cannot be divisible by p. Does this make sense?
Yes, thank you.
So there are only two numbers from this list that satisfy either this or this. These numbers are 1 and p minus 1. Since this is if and only if statement, these two numbers are the only numbers from this list that are their own inverses. Means these are the only two numbers from the list that satisfy the following property. A square is congruent to 1 modulo p. Done. Here is what we do next. So it's written, therefore, we can group the integers from 2 to p minus 2 into p minus 3 over 2 pairs of integers with the product of each pair congruent to 1 modulo p. So here is what we do. Over here, we have p minus 1 integers from 1 to p minus 1. First, let us exclude from this list the following two numbers, 1 and p minus 1. If we exclude from this list these two numbers, the remaining integers are 2 and so on p minus 2. This is exactly what is written here. Let us consider the following integers: 2 and so on p minus 2. Here we claim that all these integers can be grouped into p minus 3 over 2 pairs. Well, indeed, we will have these many pairs because the total number of integers here is p minus 1. We exclude 2 numbers, therefore the total number of integers over here is p minus 1 minus 2 means p minus 3. So we have p minus 3 integers here, therefore p minus 3 over 2 pairs. But now it's written we can group these p minus 3 integers into p minus 3 over 2 pairs such that the product of each pair is congruent to 1 modulo p. Why is that? Here's why. So pick a number from this list. Let us denote it by a. Since this number a is a relatively prime with p, the congruence ax is congruent to 1 modulo p has a unique solution. So any integer from this list has its inverse. Well, we already said that any integer from this list has its inverse. In particular, any integer from this list has its inverse. But here's an important point that we are trying to make. We claim that if we pick any integer a from this list, its inverse, which we denote by a bar, is different from a. Once again, pick a number from this list denoted by a. This number has its inverse, we denote it by a bar. We claim that if a is from this list, a bar is necessarily different from a. Here is why. By sentence number 1, the only 2 numbers from this list that are their own inverses means a bar is equal to a are 1 and p minus 1. Therefore, for any other number, for any number from this list, a bar is different from a. So, if we pick any number a from this list, a bar, its inverse, is not equal to a. Next, note that since a bar is inverse of a is inverse of a bar because inverse is unique. Of course, we are talking about numbers between 1 and p minus 1. So, if we pick any number from this list, number 1, its inverse is different from this number. Number 2, its inverse is unique. Therefore, if we pick a number from this, denoted by a, its inverse, which we denote by a bar, is different from a. And then for this number, for a bar, inverse will be A again, because inverse is unique. So pick a number from this list, find its inverse from this list, set this pair aside. Pick another number from the remaining list. Its inverse will be in the remaining list, because its inverse cannot be from the pair that we just set aside. Because if its inverse is from the pair that we just set aside, inverse of this inverse will be from that very pair. And so on. So we can split all these numbers into non-overlapping P minus 3 over 2 pairs. So here we use existence, uniqueness, and the fact that only 1 and P minus 1 are their own inverses. Next, since we can group all these integers into P minus 3 over 2 non-overlapping pairs that satisfy this, we can consider the product of all such congruences, and the product of left-hand sides will be this. So once again, remember, we split all these numbers into these many non-overlapping pairs. Say A1 comma A1 bar, A2 comma A2 bar, and so on. Each pair satisfies this congruence. A1 times A1 bar is congruent to 1 modulo P. A2 times A2 bar is congruent to 1 modulo P, and so on. Then consider the product of all these congruences. On the right-hand side, we will get the product of ones. On the left-hand side, we will get the product of all these numbers in some order, which means the product of the left-hand sides can be rewritten as this. Folks, do you all understand how we come up with this?
So since the pairs, the product, okay, so we have all these pairs, and in each pair there's 2 elements, and the product of them is congruent to 1, right? So
yes.
If we multiply those pairs together on one side and then multiply the ones on the other side, they'll be congruent. Is that accurate?
On one side, there will be the product of ones. On the other side, there will be the following product: A1 times A1 bar times A2 times A2 bar times and so on. But these numbers, A1 times A1 bar times A2 times A2 bars, can be reshuffled in such a way that on the left-hand side we'll get this. Because when we put together all numbers A1, A1 bar, A2, A2 bar, and so on, we'll get this set. All numbers from 2 to P minus 2. Because we just split this set into these many non-overlapping pairs, correct?
Yes.
By the way, this is the reason why at the very beginning we showed that the theorem is true for P is equal to 2 and P is equal to 3. In order to consider these many pairs, P has to be greater than 3. Otherwise, say if P is equal to 3, we have 0 pairs. If P is equal to 2, we cannot consider pairs at all. This is why this step is important. The rest is easy. First, let us multiply both sides here by 1, and then we multiply both sides here by P minus 1. If we multiply both sides here by 1 and P minus 1, the left-hand side becomes this, which is p minus 1 factorial. The right-hand side becomes this. And of course, 1 times p minus 1 is equal to p minus 1, and p minus 1 is congruent to -1 modulo p. This is exactly what we wanted to prove. P minus 1 factorial is congruent to -1 modulo p. Now, part 2. Let us prove that if this is true, P is prime. Let us prove it by contradiction. Let us assume that P satisfies this and P is composite. Since P is composite, P can be written as A times B, where A is strictly between 1 and P, and B is strictly between 1 and P. Here is what we do next. Since A is strictly lesser than P, A divides P minus 1 factorial. Because P minus 1 factorial is the product of all integers from 1 to P minus 1. But A is greater than 1 and strictly lesser than P. So A is in the list. Therefore, A divides this. But now, P minus 1 factorial is congruent to -1 modulo P. Since P minus 1 factorial is congruent to -1 modulo P, P divides P minus 1 factorial plus 1. It's exactly what is written here. But A divides P. Since P divides this and A divides P, A divides this. It's exactly what is written here. Now let us put pieces together. A divides P minus 1 factorial. It's exactly what is written here. A divides P minus 1 factorial plus 1. It's exactly what is written here. Since A divides this and this, A divides the difference of these two numbers. This is what we put here, the difference of this and this over here. But note that if we cancel out P minus 1 factorial, what is left is just 1. Conclusion: since A divides this and this, A divides 1. We got a contradiction because it's written A is greater than 1. A number which is greater than 1 cannot divide 1. So, at the very beginning, we assumed that P is a composite integer. We got a contradiction, therefore P is not composite, therefore P is prime.